Oh, good morning, Chunk. Good morning, Walnut.
I'm just studying for my topology qual.
All you really need to know before topology is how to deal with sets and operations on a box. Union, intersection, difference, complement, product. Look up De Morgan's laws. Don't make paradoxes! Sets and operations on set. That's all we need to start talking about topology. Chunk? Walnut? Where'd you guys go?
So the technical definition of a topology is that if you have some set X, then a topology, call it tau for T for topology, is just a collection of subsets of X, which we call the open sets. But they're subject to the conditions that the empty set and the whole set are in tau. If I have any collection at all, then their union is in tau. And if I have a finite collection, then their intersection is in tau. But that's dumb and kind of abstract, and it doesn't really convey what we want a topology or open sets to convey. So really, what I like to ask myself is, what happens when we just futz up the real numbers? It's a clunky question for sure, and it's definitely not all-encompassing, but it's historically how you can think about general topology. We have this rich theory of the real numbers. We can talk about continuous functions and compact sets, and open and closed intervals, and completeness, and connected subsets, and sequences, and on and on and on. But really, what if we just ask ourselves, what if we're not in R? What if we're not even dealing with numbers? What if there's no sense of distance, but maybe of closeness? What if we don't have limits of sequences, or if they're not unique? These are all interesting questions. And if our space isn't R, and our open sets aren't, well, open intervals, then the answers can be quite surprising. The definitions in topology often come from the idea that we should impose the minimum amount of structure to see what sort of interesting things happen. There's a ton of structure on R, so what happens when we're not in R? We'll begin to answer that question when we start to develop some more definitions. Every time we define some property of a topology, it's often a very good question to ask, how is this like or unlike R? But for now, let's return to the definition of a topology tau on a set X. The first thing you want to do whenever you have a definition is to try to come up with some examples of that thing. So, what are some examples of topologies? Well, if we go back to the definition, let's start with any old set X and put a topology tau on it. What should be in our topology tau? By definition, it needs to have the empty set and X itself. And let's stop there. It turns out that this is enough to have a topology. No matter how we take unions of the empty set and X, we'll only ever get, again, the empty set or X. And if we take a finite intersection of empty sets or X's, then we'll only get the empty set or X again. This is called the trivial topology, because mathematicians use trivial to mean like the simplest example, or something always holds, or when you're in a proof, obvious, as opposed to in everyday speech, where trivial often means unimportant. The trivial topology isn't unimportant. In fact, far from it. It's often sometimes a good first example to check a definition against. It's just as simple as a topology can get, because it has the bare minimum of necessary open sets. So let's think of some non-trivial topology. Given some set X, which subsets should we declare to be the open ones, such that they're closed under arbitrary unions and finite intersections, and therefore form a topology? Well, if the trivial topology is our simplest example, at the other extreme, let's just toss all those bad boys in there. Basically let tau be the power set of X, or any subset you like is open. We can check easily that this forms a topology. The empty set and X are both in tau, since they're subsets of X. Given any subsets of X, their union is in X. It's not like you're going to suddenly jump outside of the set. And given finitely many subsets of X, their intersection is a subset of X. This topology is called the discrete topology. That's because you can think of open sets as declaring closeness in your topological space. If every set is open, all the way down to the singleton sets, then no point is really that close to any other point, and your topological space is just thought of as a discrete collection of points. On the other hand, the trivial topology basically just lumps everything into the same neighborhood, smushing everything together and screaming, "Everybody's next to everyone!" It's the difference between cramming everybody on Earth into one apartment versus giving them each their own planet.
So a natural question to ask is, if there are open sets, Are there closed sets as well? And the answer is yes, but be careful. So a closed set is not a non-open set. Instead, we define a set to be closed if its complement is open. So a set A is closed exactly when x minus A is open. Now, depending on the topology, sets can be just open, just closed, both, neither, or, well, that's exhaustively everything. Just be careful, because sets aren't doors. They're not either closed or open. Hi, Chunk. It turns out that you could define a topology completely in terms of closed sets. It's not super important, but it's an easy exercise to show that it's an equivalent definition to declare that the empty set and X are closed, that the closed sets are closed under arbitrary intersections, and that the closed sets are closed under finite unions. Here's a hint. Did you do last week's homework? It does give us good motivation for our last example for today. It's called the finite complement topology, where we declare a set to be open if its complement is finite. Or, as we've just seen, an equivalent definition is that all of the finite sets are closed. Today's homework is to show that this does indeed form a topology. So check off those 3 conditions, and I'm grading that homework, so you better actually do it. I'll know. That's all for this time. See you guys next time. Say bye, Chunk. Bye-bye.